Hey there, welcome back. Today's video is going to be a little bit of a departure from the usual format. I was going to live stream this, but I get interrupted too much during the day to really live stream something, I think. So what I'll do is I'll record all of this and edit out the interruptions and things like that, but generally I'll just won't do a whole lot of editing work to smooth it out. So it should be fairly rough. If you have any comments, questions, go ahead and leave them down below. If it's a topic that is of interest, again, go ahead and leave a comment. Speaking of topic, what I'm going to do today is I'm going to talk about creating a driver for a peripheral for a Meadow device. Basically, adding something into Meadow Foundation for a peripheral that doesn't exist in there. As a little bit of background, I'm going to be creating an automotive project here, probably this winter, where I am going to read sensors that are effectively variable resistors. I'm going to have different sensors that have different resistance ranges, so I need to build something that will allow me to bench test those without having to have like a temperature sensor that I put into boiling water and things like that on the desk. I want something that's a little bit easier to work with. So basically what I need is a variable resistor or a potentiometer or a rheostat, however you want to look at it. I've got a couple of options here. So the obvious one is I could go with something like this, right? Just go with a potentiometer that I turn it and the resistance between the wiper and one of the legs changes. That's all great and it would work, but I want to be able to drive what that resistance is and know what it is. So I really want something that's more programmable and so that I can read back what I have. So the other option is, and I've already got this wired up because I cheated a little bit. Basically, I've got this. This is an MCP41. I'm looking over here because that's where the data sheet is. This is a 41, I think 62, 4152. At any rate, it is a digital rheostat. It's different than a digital potentiometer somewhat. We'll talk about that when we look at the data sheet. But basically, I want to be able to write to it to set a resistance value. This one works over SPI, so we're going to look at building an SPI or SPI, I may call it that as we're running, create a driver for Meadow Foundation so that I can drive it from this Meadow. As with all of our Meadow Foundation things, it could also be driven from Linux, can be driven from Windows, can be used in Raspberry Pi, Jetson Nano, a lot of different things. I'm just going to be using the F7 to test this out. I could use the desktop development environment, but it doesn't really make a whole lot of difference. So let's go through the process of looking at the data sheet, figuring out exactly what to write, how to read the data sheet, how all of this works, and how I turn this into a library. And in the spirit of cheating, you can see I've already created a solution with a couple of projects. There's nothing magic going on here. I have a class library that is this 4XXX. The reason it's a 4XXX is those three X's could be different things. There's a 2, 3, 4, 5, and 6, I believe. Basically, there's a whole bunch of these. These numbers designate how many of the rheostats that it has built into the part. Another one is whether it is a rheostat or a potentiometer, and another one is the number of bits of resolution it has and whether or not it records the last setting into internal memory. So when it starts up, it either starts up at the last setting or it might start up at mid value. Additionally, there is a dash number on all of these that for the part. They come in, I think, everywhere from 5K to 100K, maybe even bigger than that in resistance. So the reality is the number of parts you can get in this series is rather large. In fact, I bought an entire bag of a bunch of different parts, so I've got a series of them. They're all the single channel because they're DIP format. They don't have dual channel in the DIP format, but there are different resolutions, different resistances, things like that. The idea is I want to have a single driver that will run every one of those parts. So again, I've got this project here. It has a empty class library in it, and then I have an application. This is a Meadow application, but it only has an initialize and run, and they don't do anything. So I am basically starting from scratch. I just didn't show building a project and adding a couple of, or building a solution, adding a couple projects to it, because, well, that is not really what I'm trying to focus on here. Next thing we need to look at is the data sheet for the part. So this is the data sheet. It covers all of the parts. So we know, looking at it, that it is a SPI device. So the first thing we need to do is I'm going to go create a class and build in some of the scaffolding for an SPI device. So first things first, we're going to come over here and we're going to change the namespace because I want to put this into Meadow Foundation. And yes, I'm cheating. I'm copying and pasting from another project. And I want to make this language version 10. So we're going to change this to an MCP4 XXX. And rename the file. This will be a base class for all of my other pieces, right? So we're going to make it abstract. And I'm going to implement the SPI peripheral from Meadow Foundation. And you can see, if I can find my mouse, in the dependency chain here, I've got Meadow Foundation. I'm referencing a beta, doesn't really matter. This has been around for a long time. I'll auto implement this. And we go, okay, well, the first thing I want to look at is the default speed and the default mode. If we go back to the data sheet here, it says here that it operates up to 10 megahertz. And if we look at modes, it supports 0, 0 and 1, 1. So I'm going to do a default mode we're going to do is mode 0. And we'll bring the default speed to 10 megahertz. I'm going to replace the setter and getter for this. So one of the things that makes things a lot easier, if we're implementing a SPI peripheral, we have a SPI communications library, or base class, I guess, that is useful. It will implement a lot of these bus read and write things for us. So we can just kind of bring that in. And once I bring that in, I can then take the two properties here, the mode and speed, and just have those as pass-throughs from that SPI comms. So we have now implemented this entire peripheral. The next thing we know we need is we need a SPI bus, and we need a chip select for enabling it. We also know, let's just start there. We know the few other things that are probably going to have to come in here based on the fact that we're doing multiple parts. Like some of them may have one, some of them may have two different resistors built in. But let's talk about that when we actually get to it. Initially, we know we need this. And we're just going to pass through the bus that is given to us, the chip select, and the bus speed. Just like that. So that builds it up from our default mode and speed, given a bus and a chip select to drive these. All right, the next thing I'll do is I typically go to the data sheet and I want to look at the communications with the part, look at the commands and registers, things like that. So let's take a look at how this guy works. This has all of the, typically a data sheet will have, this is how SPI or I2C work. If you understand how they work, you don't need to look through all of that. It's usually boilerplate stuff that's copy and pasted. There is something a little bit wonky here on this part, but we'll come back to it. It's weird. It has a full duplex in communication of just a couple of bits. Again, we'll come back to that. First thing I want to do, though, is look at what are the commands that we can send to the part, what are the registers or the addresses where those commands go, that type of thing. So it looks here like we've got a couple of commands. We've got read and write data, and we've got increment and decrement of the wiper. It's got both 16 and 8-bit commands, which is a little interesting. So we've got the command here. It's got some data. What the command is gets shifted over, and we've got a memory address. The memory address is probably the register. So we come down a little bit further, and here we've got the addresses. Looks like you're setting the wiper, so the resistor on this, and we've got 0 and 1, 0 and 1 for the parts that have 2. And then we've got a couple reserved. We've got this TCON, which is the configuration register, and a status register. So pretty simple. Looks like we have 1, 2, 3, 4 addresses to write to. It's nice that they give us the data string here that is on the output and the inputs and what the data looks like. It says it's 10 bits of data, but it's only 9 bits wide, which is fun because it's even 9 bits puts us 1 bit into the other byte. This will become important. I previewed and looked at this datasheet a little bit before I started recording. Got some error conditions, commands. We can do continuous commands, which is where we send it a command and then add another one. So let's say we're doing decrement or increment. We could just go increment, 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 all in one SPI transaction where we basically hold the chip select to activate and just continually set it. I'm not going to support that in the initial version because I don't really need it. Really, I just want to say, this is the resistance I want. So we want to set the wiper to a value based on some parameters around the part. So I really want to say, I want, 1200 ohms of resistance. That's what I want my driver to take in, and I want it to turn 1200 ohms of resistance into the commands that send out to the part so that we can get that back. So the important thing there is we know that we have to send a command to either wiper 0 or wiper 1. So when we create the part, we have to know if we have multiple wipers to deal with that. So the first thing I'm going to do is I'm going to come over, if I can find my code again, we're going to create a wiper class. This isn't going to be used anywhere outside this part, so I can actually just use an internal class on this. We know that we want to be able to basically set and get its value, and we know that it is a 9-bit value, so we need at least a short to do that. And we know from this, so we have a configuration register. And let's see if we can find what that does. Where are you? Tcon, decrement, increment. It's here somewhere because I already looked at it. Oh, where are you? Aha, here we go. So the configuration, it has resistor 0 and resistor 1. In fact, it's calling them resistor, and then we can read the wiper or the terminal on each one. So let's actually change the name that we have here. We'll call this a resistor. And the configuration register is actually common to both, which is a bit of a pain in the ass, but what do you do? So I want to be able to, the configuration register is a single byte here. So we want to be able to read and write. I made them private because I suspect that the resistor is only going to need to be able to do it itself. Now, in order to be able to do any of these read and write operations, we need access to the bus. So we're going to create a constructor for this. And we need to know which resistor it is. So we'll have an index. There was here resistor 0 and resistor 1. So it's using 0-based indexing. We'll do the same. Just like that. All right. So now we have our internal resistor that we can set, get the wiper and the configuration. Next, we actually need to implement some of these. So let's go take a look at the commands again. First, let's look at the configuration. What does that do? Basically, we've got these the high 4 and then low 4. And if we look, well, first of all, we can look here. They're all read-write, except the first one is only read, but it says it's reserved. And if we take a look, 2, 3, 4. Interesting, it actually says it's 9 bits, but we only use 8. Strange. We're just going to use 9. I'm not exactly certain what it's doing, because if we take a look at the way that this works in commands, reading and writing, the configuration is... so it is a 16-bit read, but we only care about the last bit. Again, all these parts that you'll run into, they've almost always got some sort of little weird configuration or little strangeness about them. It's just something that you have to get used to as a software developer when you're working with these. So it is 9 bits, but we're only going to use 8 because this one is reserved and forced to 1, so I don't really care. These 8 are all read-write, and they all default to a 1. So if we look at the legend, RW, it's a readable and writable bit. And then it's got this -1. -N is the value at POR, which is power on reset. So it is 1, which is set when it powers up. So basically, this powers up and all of these are set to on. And if we go take a look at what those mean, 1 means it's not forced into shutdown and the resistor is connected to the network. And so basically these just allow you to disconnect the ends of the resistor. This would be handy if you were doing something that was low power and you wanted to stop current flow, like while it's asleep. So the reality is we probably don't need this at all. I will at least leave the commands in here to be able to read and write them. But for my application, it's going to come up enabled, and I'm going to leave it enabled. I'm never going to want to disable these. So the reality is the TCON read and write, I probably won't even need. So let's go take a look at setting and reading the wiper, which is something that we need to be able to do here. Come down and take a look. Okay, so we have this write data. It has, again, it's a 16-bit command for read and write. So really right now, all we're concerned with is the 16-bit commands. We have our data. Our command is left shifted 10. It's 2 bits. And then our address is left shifted, looks like what, 12? And it is 4 bits. And the address is, so our command is 1100, and then our memory address is this here. So 0 for reading, writing data for the wiper, or 1 for resistor 1. So let's take a look again at our code. We know that we would have some constants that we need to be able to do, right? So we know we've got read data and write data. So a write is a 0, a read is a 3, and we know that that is left shift 10 on a 16-bit command. So if we come over here and we say the resistor, we know that the data, sorry about that, we know that the data is 10 bits. It's really only 9 bits because it said somewhere around here. here that the data is only 9 bits wide, so the MSB is ignored by the device. So it's only a 9-bit field, so we want to be able to create something that we can mask off everything else. So I'm going to create a data mask that is 9 bits. Right, so to get 9 bits of all ones, you take 1, left shift 9, and subtract 1. If you don't believe me, let's fire up the calculator. Just to verify that. So if I go 1, I left shift it 9, that gives us this, right? Which has, here's 8, 9, it's the 10th bit is on, which would be 1 left shift 9. But if I then subtract 1 from that, it turns on 9 bits of data. So that's all I'm doing there. And where did my cursor go? There it is. All right. And then, so we have our data mask, we have our commands, and then we have our memory addresses. So for wiper 0, it's a 0. So I could just use a 0, but 0 isn't terribly readable to me. So I'm going to create a constant for it. And wiper 1 is 1, but those are left shifted 9, 10, 11. So those are left shifted 12 places. So that gives us those command positions there. And let's see, we already decided we're not going to really look at the TCON because we're just going to leave it all on. Let's look at status register. What does that have? Status register is probably back up here as well. TCON and status register. Reserved. Whether or not we are shut down, so we can actually put the part into a shutdown state. It disconnects and forces the wiper to terminal B. We're not going to be using this for my application, so I probably won't implement this, at least not in the initial version. Definitely not for this stream. These are all reserved, and 8 through 5. So basically, everything is reserved except 1 bit for the shutdown, and I don't care about shutdown, so we can ignore that command as well. So nicely, really all we need are the commands for setting and reading the 2 wipers, which is fantastic. So now I can actually come down here to our read and write TCON. We don't care about those. Not going to use them. All right. So if we're going to set the value, we have to be able to write data. Now this is where it gets interesting on this part. Let's take a look. First, we know, the first thing we know looking at this 16-bit is that, this is byte 0 and this is byte 1. So it's actually big endian, not little endian. So we have to do bit swapping when we're doing our stuff from ARM architecture or x86. Basically, from most things today. So we need to create a command for this. Let's create the command. We know that it has to be a short And we know that it's our value. I can spell value. We're going to AND that with our mask, right? Then we have to turn on the command for writing, right? So we're going to OR it with the write data command. And then we need to OR it with the address, and it's either 0 or 1. So we're going to OR that with if index is 0, then and C# really sucks for doing bit manipulation. It just always wants to coerce everything to an int, so you have to do all these casts. But, so what we've got is, we're going to build this command up. It is the data ANDed with our 16-bit mask. So that takes this piece here, right? And make sure that anything outside of that is zeroed out. And then we're going to OR that with our write data, which is, it's a 0, so it doesn't really do anything, but it makes this way more readable than ORing it with 0. But our write data is 0, left shifted over into this command. And then we OR that with the address, the memory address, right? So the memory address is either 0 or 1, left shifted 12 over here into this address. So if the index is 0 or 1, and while we're here, I want to make sure that that is protected. And we could do a switch. We could do an if. Yeah, let's do an if. That'll just help protect us there. All right. So we've built our command, and then we just need to send that command. So let's turn it into a couple of bytes. We're just going to build these right on the stack. We don't need to use new. I like to use TX and RX so I know which direction it's going. So we have a couple of bytes. Now let's stuff the command bytes into this. Again, remember we've got little endianness here. And so we want to right shift this 8 because, again, the endianness, we need to take the one that's on the left as a short and push it over. And the second one is just the right-hand byte. So that gives us our buffer. And now we just need to write this out. And that's all there is to it for the write. We just create the command and send it. reading is going to be really, really similar, right? All we're going to do is create a command, send it, and then read the data that comes back in. But let's go take a look at that data sheet real quick. This is one that if you weren't looking real close would probably trip you up. Right? Where is that? Yeah, here it is. So look at this. This is fun. Here's our command byte, and look at this single read. It says in here, the first 6 bits determine the address in the command, which we already know. The 7th clock will be whether or not it's an error, so I'm not overly concerned about that right now. But the read operation, yeah, requires that the chip select go low. Where is it? I've read it in here. Here it is. The SDO, so the data out, starts driving data on the 7th bit. It doesn't wait until a full byte has come in. It starts giving you data back while you're clocking data to it. So while you're sending the command, it starts sending data back. So this is a full duplex, not a half duplex, which is an unusual behavior for typical SPI devices. So these are the types of things that make doing driver development really frustrating, where you'll be pulling your hair out trying to figure out why it's not working. And it's because you get little behaviors like this. So when things are not working, go back to the data sheet and read carefully again. This picture shows it pretty well. So we have the command byte and the data byte, which is 16 bits for our full command, right? And then the data that's coming back in starts coming back in while we clock this out. So really what we need is we need 2 bytes out, 2 bytes in. SPI works that way. But we need to write these and read at the same time, and then take the data that we read at that same time and turn that into our thing. So we can't send 2 bytes and then read 2 bytes back. That is not how this works. We need to send 2, and then while we're sending, the data coming back in is the data that we want to look at. Again, it's a little confusing. So let's go take a look at how we would implement this in the driver. So we know that we're going to do a command basically like we had done before, right? In fact, we're just going to copy this one. And we're going to read instead of write. And not totally obvious at all to me. In fact, it's a little frustrating that they don't tell us on a read data, right? It says we send, this is our read command. This is our, actually, I guess this is our read address. This is the read command. So address 0, command 1, 1, or 3. And then it's got these ends. And it doesn't say what these should be. Should these be zeros? Should they be ones? I don't know. But this part seems to be biased toward ones. So it looks like on is the default or the reserved state. So what I'm going to do, just for my own sanity, is I'm going to start with ones as these ends. They probably don't matter. It probably is just looking at the clock, but we're going to turn on these 8 bits here, these over at the right. So we're going to turn those on to 1. Now that's 8. It has a 9th and a 10th, and the 9th, I think, is not used, and then the 10th is the error. I don't know. We're just going to give this a try, see how it works anyway. If we need to turn on or off some of those, we can. In fact, we don't need this data mask, right? Because we're just doing a read. All right. So here's our command. Now what we need to do is we need to call a read. So we need 2 buffers. We'll just steal the logic from up there. And our receive buffer is just 2 bytes. And so now we're going to do an exchange on the bus, which says send to and receive to, and we're going to use full duplex. So the key here is that full duplex. It's extremely important. And then our value, we need to convert back to the endianness that we want. And we have to cast it to a short. So that takes care of the endianness. And then because we're bringing back 16 bits, and it says when we do a read, it's going to have all of these high bits on, and we know that the 10th one doesn't matter. At any rate, we want to get rid of all of this chaff up here at the upper end because we know that it's not valid for the data itself. So we're going to AND that with our mask, we're going to AND that with our data mask. Okay, so that should get our wiper value. So we now have the ability to create this resistor and set and get its wiper value. Next up, let's take a look at how we consume that in our MCP class. All right, so consumption. We know that when we create the base class, we need to know how many resistors it has. And then we need to create these internal resistor classes based on that. We might as well add a parameter check here as well. If I can find it. That's probably a little bit easier to read. In fact, I like that better. So we'll come down. All right, so when we create this base class, we tell it what our bus is, what our chip select is, and what our resistor count is. All right, so now this resistor, I don't want the user to, be calling set wiper. That's why this is an internal class. We've got, things like set wiper and get wiper, which aren't terribly useful. What we really want is we want set resistance and get resistance, right? So what we'll do is we're going to change these to, let's call those internals, right? Basically, I'm trying not to leak things that the user doesn't care about or shouldn't know about. And so I'm trying to roll through that in my head right now. So let's make these internal. All right. So now really what we have, we've got this base class, which is abstract, which has our number of resistors, and the resistors have the ability to set and get the wiper internally. So publicly, we need a couple of methods. For resistance, we'll just do it as a property. And really, we need to know a few additional things here. It's not real obvious until we create a concrete class. So let's create the one for this part that I have on my desk, which is a 4162. We know the 4162, the one in it, says that it is a single resistor. Now, to 4162, the 6 tells us what the max number of steps are. If I show you that in the data sheet, let's go all the way to the top. It'll explain all of the parts. So here we go. I've got a 4162. So we've got the number of potentiometers or a number of pots in it, right? We also have the number of steps, basically the resolution that it has. It also has Does it store it to RAM or to basically EE, which is persistent? So it'll either come up at mid-scale or whatever the non-volatile wiper was. So really what we need to know, and oh, they also have the typical or the resistance options of 5, 10, 50, or 100. So we've got a pretty large matrix here. But the 4162 we know is a potentiometer or rheostat. So really, I feel like we need a couple other abstract classes here. That'll just help us to define whether or not it's a rheostat or a potentiometer. Both of these are derived from our base. All right, so that gives us that. Now we also know the number of steps that it has to have and our max resistance, right? So let's put that into, it's really a behavior all the way down here, isn't it? So in order to calculate resistance, we need to know what the maximum resistance is. And we need to know the number of steps so that we know how many ohms per bit in that wiper read or write we have. If you follow me. So we actually need to pass these down to the resistor. And the base classes here need these as well. Hopefully this will make sense in just a moment. Since we don't know exactly, I don't want to create a 4162 for all four of the resistance values. We certainly could, do a -50, or I think that's how they. Yeah, I'd have to go take a look at somewhere else in here, but I think it's -5 or -50 is the 5K version. At any rate, we just let the user pass in this resistance. You know, you could make an argument that there should be a class for each one, though that would make the matrix of the number of classes in here really large. So let's just start with, we'll just pass in the resistance, right? But we know that the number of steps is based on the part number. And the 4162, 4162 number of steps is 257. I don't really like that. We could also make that an abstract property. There are a few different ways to architect this. Maybe an abstract property is a little cleaner, but this should get us there, right? So now we're passing in that resistance. The resistor count, we already know is 1, so we don't pass that in here. So when you create the 4162 class, you're going to give it a bus. You're going to give it a chip select. You're going to say, this is the 5K part. I like that. It passes it down to the 4xx2, which tells us that it's a rheostat. And so we will probably add, I'm not going to do it right now, but I will probably add something like that to this so that we could do an I rheostat here. And a potentiometer there so that we could differentiate between them in some cases. Also, the rheostat does have, in fact, if we go back and look at the configuration register for this, the rheostat and the potentiometer are slightly different. The rheostat, you can't disconnect one of them. I think it's A on them. Yeah, here it is right here. So if you look at the rheostat, you've got the wiper and B, but on the potentiometer, you have A, B, and the wiper. So if we flesh out the ability to do disconnect and connect, we do need different implementations anyway. So that will help us to be able to do that in the future. So we know that this is a 2, so that informs that it's a rheostat, and that informs us that it's one of these. All right. So that passes all that down. So really all we have to do now is calculate or do a translation between resistance, which is a Meadow units for ohms, and the wiper value based on the number of steps and the total or the maximum resistance of the part. I know, confusing. I'm hoping that I'm making myself clear. So let's see, if we want to convert, let's see, let's first do the get, right? And so really we're going to get the wiper value, right? And so the wiper value gives us, it's not unitized, but it's basically bits, right? And then we know that the maximum resistance divided by the number of steps, so let's say it's a 5K with 257, so 5K divided by 257 steps is going to give us resistance per step. And if we multiply resistance per step times the number of steps, or the value that we're getting back from the register, that will give us resistance. So return new resistance. which is our, I haven't stored that yet. I actually want to, because the resistance and the resolution is common across the whole part. I know this is a little wonky sometimes. So I'm just going to make this protected to begin with. So I'm going to set these here. And then I'm going to path the parent, the actual MCP, to the resistor. Ugh. There we go. So now again, we can take the max resistance in ohms, divide that by the parent non-resistant with split steps, right? Take those and then multiply that by the wiper value that we read. And that is a result in ohms. And then setting is really the same thing, but we want to invert it because we want to convert to the number of steps. So we're going to create a W that we want to write. The W we're going to write is a short, and it is the parent's max steps divided by the parent max resistance ohms multiplied by the value that we're trying to set in ohms as well. And then we want to set wiper to that value. And again, C# and its bit manipulation there. Convert to a short. All right. So that should be, in theory, all we need to do. Let's go take a look and see if how the API looks from a consumer perspective. Let's go take a look at how the API looks from a consumer perspective. We have a reference to the F7 and to the MCP project. Okay, so we want a $41.62. We want our SPI bus. We're going to hook it to, say, D15. Just an arbitrary chip select. As long as I wire it up that way, that's fine. The part number that I have is the 5K version. Try to at least decrease some of this. It doesn't take a pin, it takes a port. And it'll be active low, so we'll start high. All right, so that should create our MCP. And then consuming it, let's take a look and see if what we did looks okay. Got those. We know that this is a single resistor part. And it's a 5K, so let's just try this. And let's actually expose that max resistance. Where did it go? It's over here. Let's make that public. There's probably no reason not to make that public as well. Also no reason to misspell it. Come back here. Yeah. So we'll just start at the low end and step up 500 ohms every time and try to write that, right? So that should do that. Let's output it so we can see what it's doing. Okay. So we're going to start at 0, go to the max resistance, stepping 500 at a time. 500 is pretty big. We're going to hit it pretty quick. Let's just step 100 at a time. Create a new resistance, output what it is, and then set the resistance. So we should be able to hook a meter to this, to the wiper and whatever it is, pin A, B, I don't remember. I'd have to go look at the data sheet again. The other end of the resistor anyway. And it should walk through all of this until it's done. And we'll do this. All right. We haven't even built yet. Let's try that. Build. Oop, didn't blow up. That's always a good sign. All right, let's connect up to the hardware. And see if I can get all of this in on camera. Connect these up. Ugh, come on now. Set that to resistance. And actually, let's take a look here. I think we're going to want to see the output as we run this. So let's deploy this to the device. And of course, the camera is sitting right on top of what you need to see. Let me move that over there. All right, so we're pushing our files. You don't need to see all this, so I will just fast forward through that. Oh, yeah, that would make a difference. I mean, it's at 4.93K, so it's at almost 5K, which is good. We should probably put in some sort of a time delay here, right? Let's wait a second or so between each one. It's probably a little bit more reasonable than how fast can we do it. Redeploy. On the plus side, it seems to be stopping pretty close to 5K. Now remember, there is a tolerance, so it might not be exactly 5K. It might not drive down to 0. I'm sure it won't drive down to 0 because that would be a short. The other thing to keep in mind is we're stepping by 100s, but it is got a resolution of 5,000 divided by whatever it was, 257. So you can't get an even division by all of these. But it should be at least reasonably close. All right. And it looks like it's jumping by roughly 100 every time. So 1,000 is 1,100, 12 is 13. So looks like on the low end, it turns out to be about 100 ohms higher than what we're asking for. At about mid-range, it's pretty darn close. Yeah, that's really close here. And again, this is skewed slightly because it doesn't drive all the way to 0, because if it did, it would be a short circuit. And then all the way at the top, see, 5,000 ends up with 4920. So really close. So there you have it. We have done a driver for a part. It is an extensible driver, so we can go ahead and add all of the other parts. I will probably go in and add things like that configuration register to allow us to disconnect and reconnect resistors internal to it. I may even add the ability to turn it off. But from a functional perspective for what I need in this upcoming project, this works. And it's at least extensible, right? We could go in and create, oh, hold on, let me. So, so there you have it. We've got this functional driver for an SPI device. It is extensible. We've written it for the 4162 here, but if we take a look again back at the code, the 4162, we could change this to like the 4262. We would just change this to a 2. And we could change it to like the 4152. I don't remember what the difference is, but let's say it's instead of 257 a different value. We could change the number of steps. So we could create a bunch of these different classes, and we could create some that are potentiometers as well, all based on this single driver. That's it for today. That is a quick overview of creating a driver for Meadow from scratch, this one using SPI, but the procedure for doing something like I2C would be very, very similar. So that's it for this stream. Again, if you find this content interesting, go ahead and leave a comment down below. I don't know exactly what people are interested in and what they're watching. I can definitely do more of this, or I can do more building actual projects. So until next time, thanks for watching.